But why am I finding fx and f? Does it give you the function, by the way?
No.
Oh, you have to use the diagram, so I need to go get the. It's a vector, right? And it's going to be fx at 3, 1, comma, fy at 3, 1. So we need to do both of these. And I like going behind and going to the front. So fx means what's changing. If fx means which variable is changing?
X.
So what's fixed?
Y.
Y. So if we fix the y value, is that a horizontal or a vertical line?
Horizontal.
So we're looking at the rate of change like this, right, for fy, correct? So if we label some points here, you know, we know the exact values here and there, right? Correct? So fx 3, 1 is going to be equal to what? 2 minus 1 over 4 minus 1. So that's going to be 1 over 3. And then fy at 3, 1, what's fixed now?
X.
X is fixed, correct? So x is fixed, so we're fixing this right here, correct? And what do we have for known points here? How about we go to there, and we go to there, right? So if y is increasing, so that's going to be 1 minus what? 3?
3.
Over 3 minus 0. Good job. So negative 2 over 3. So this is going to be equal to 1/3, comma, 2/3. So our grad f is going to be equal to 1/3, comma, negative 2/3 dot what? Whatever that, what's the u value? Right there. So just like negative 2, 1, and then what do we multiply the whole thing by? Root 5. Doesn't matter where that root 5, oh, just divide it by, right? Doesn't matter where, can we pull that out? It's totally legal to do that, right? Because when you dot something together, it's a scalar, you're going to just multiply it by, or divide it by root 5. So what are you going to end up with here? You're going to end up with negative 2/3 plus negative 2/3 over root what? 5. So what are you going to end up with? Negative 4 over 6 root 5. So negative 2 over 3 root 5. Did I do that math right?
Yeah.
It's going to be equal to 3 times negative 1 squared times 2 squared. So it's going to be 12, right? So therefore, grad f of negative 1, 2 is negative 16, 12. What's interesting is this question specifically asks, in the direction of the maximum rate of change, a vector gives you a magnitude in a direction. So this is theoretically, how many different answers could you give me for this question? An infinite number, any scalar multiple of this, right? Like theoretically, you could factor out a 4, right? So you could say that the answer really could be k times negative 4, 3, right? I've just reduced it to their, they're called relatively prime. 4 and 3 are why are they called relatively prime? Why are the numbers 4 and 3 called relatively prime? It's a term you probably haven't heard before, but I bet you can figure it out. No.
There aren't many numbers that...
Is negative 4 prime?
No.
No. Is 3 prime?
Yes.
So it has nothing to do with whether or not the numbers themselves are prime or not. Do they share any factors? No, they're relatively prime. You're going to that's a key term in number theory, relatively prime. Like 17 and 32. There's lots of factors of 32, right? Or like 9 and 64. You know, there's lots of factors of each, but do they share any factors? No, they don't. Okay, so we found the direction of the max rate of change. Great. What does B ask us for? What direction does grad... Oh, sorry. In the direction of the minimum rate of change. So what's the min rate of change? Min is going to be the negative grad of f negative 1, 2. So what's that going to be? Negative k negative 4, 3. Like that. Or you could say k fourth negative 3. Whatever you want, right? Just the opposite direction. Okay, and then C asks, in the direction at which the rate of change is 0. So 0 is going to means what? Perpendicular to the grad, right? So how do you find a vector that's perpendicular to another vector? You know, this is the straightforward, when you're in 2 dimensions, there's a really straightforward way to do this. What's the first thing we learned at the beginning of chapter 14? What's that? Ah, okay, so how do you find out if 2 vectors are perpendicular to one another? Not multiply, stop, don't say multiply. The dot product is what? 0. So you're looking for a vector, let's say AB, that when you dot it by, does it matter, Does it matter which one I take, 4, 3, or negative? Does it matter which one I take? Because they're perpendicular to these is the same thing, right? It doesn't matter which direction, because you can go that way or that way, and they'll both be 0. So how about negative 4, 3? Does it matter if I use the k or not? No, the k doesn't affect it. What is the dot product of that? Negative 4a plus what? 3b. And we need this to be equal to 0. Now here's the thing. The reason this is challenging, and you're not the first class to come up with against this, the reason this is challenging is you can choose any values you want that make this true.
So A could be 3.
Literally, a could be 3 and b could be 4. So ready, our perpendicular vector is going to be 3, 4. Yeah. Or negative 3, 4. No, you can't do negative 3, 4. You could do negative 3, negative 4. Sure. But right there it is, 3, 4. So the answer, what's the representation of any perpendicular vector? We'll call it c times 3, 4, right? Any scalar multiple of 3, 4, when you dot it by the other one, will come out to be 0. So therefore it has to be perpendicular, and perpendicular to the grad means the rate of change is 0. That's it. Does that make sense? So that's the direction you're going in. So what's the first thing you need to figure out? The actual direction you're going, right? We need the direction. So what's that direction going to be? 0 minus 1, comma, 1 minus 1, comma, 1 minus 0. What did I do there? I just subtracted, I paired up the terms. You have to figure out what the directional vector is, right? So what's v going to be equal to? What direction are we going in? Negative 1, 0, and what? 1. That's the direction we're going in, right? So it's asking us specifically, find the directional derivative. So how do we find the directional derivative? What do we need to find? We need to find grad of this function, right? And as I said in the last class, this is just adding one more bit, right? There's no method that changes. So now what we're doing is, we know that we need grad of f of x, y, z. What does that equal? Fx, x, y, z. Fy, x, y, z, and what's next? Fz of x, y, z. Nice. So then after we find that, after plugging in, okay, nice, okay. Do you want to do this out? Sure, why not? I'm going to pause it here. What, 1, 1, 0 is what we came up with, right? There's the 1, 1, 0. And what do we dot it by? Negative 1, 0, 1 divided by root 2. So what's that going to be? Negative 1 plus 0 plus 0 divided by, so what's that going to be? Yeah. Voila. That outputs a z value where you plug two things into z. Usually we're plugging in, most commonly, x and y. You plug in x and y into the function and you get out a z value. We could be plugging in a t value into a function, let's say x of t and y of t. But in this case, instead of calling it x and y, what are they calling it? It's right there. The letters are literally right there. G and h. So the function g and the function h are generating the two input values to the function f. So what's going on here? T, I got to go off the highlighter here. It's going to be real hard. T is getting plugged in to g and h, and those two things are generating what? They're going into the function f. Yeah, we're calling this function f, and it's generating z. You're plugging t into g, which gets you a value for your first input. You're plugging t into h, which gives you a value for your second input. And what are you getting out? A z. Now here's the thing. We now we've become untethered from one variable, meaning t is a single variable that's going into g and h. How many variables could theoretically go into g and h? 2, 3, 4, 5. There could be more, right? How many could there be more functions than g and h going into z? Yeah. Instead of fxy, we could have fxyz. And how many different values could be going into each of those? As many as you want. We have now opened Pandora's box in terms of how many input values could we have at each level? Multiple. As many as we want. As many as we want. And it's really not anything new. We just have to be careful about keeping track of what we need to keep track of. So what do I next level? Instead of the input functions g and h be in terms of t, they could be in terms of u and v, v and t, u, v, t, w, x, y, z, a, b, c, d, e, f, g. It doesn't change the math. It just means you have more to keep track of. So the first thing we're going to look at is this first generalization right here. G is written in terms of u and v, h is written in terms of u and v, f is written in terms of g and h. G and h. Are you with me so far? Nothing has changed. We're just breaking open the composition. Real careful about this. What does delta x mean? The change in x, the actual change in x, right? The change in x. So like how much x has changed. Are you with me so far? It's how much x has changed. What's delta y? How much y has changed. If we wanted to find those two things, and keep in mind, x is written in terms of t, and y is written in terms of t. How do we figure those things out? We multiply the slope times the change in t, the slope times the change in t, but we have two different slopes. What are those two different slopes? dx dt and what? dy dt. This is the rate of change in terms of t, the rate of change of x in terms of t, and this is the rate of change of y in terms of t. So theoretically, I could say the slope is 2, but if you want to know how far up you've gone, you need to know the change in t. Like, how long have you been traveling for? Are you kind of with me so far? So we're staying just in one dimension right now. This is single variable calculus right here. If you want to know how much change in terms of how much your delta x is, you need to multiply the slope in terms of x times your delta t. Your slope in terms of y times your delta t. Are you with me so far just on this line right here? Are you okay? You've kind of seen something similar because you've looked at parametric equations before. You need to know how long you've traveled for. So this is how long you've traveled for, and what are these? The slope, like how fast you're changing. You need to know how long and what the slope is. Are you with me so far? Oh, that differential is right here. The amount you've changed is fxab times delta x, fyab delta y. What's another way to write fxab? Z over dx. What's another way to write this? This is just notation. What is that? Partial z over partial y. So what are we looking at right here? We're looking at that delta. Delta z. How much the z has changed. Are you with me so far? But what do we know if x is in terms of t and if y is in terms of t? What did I say we're dealing with right here? What do we now know? What does delta x, where is it? Oh, it's right there. And where's delta y? So what do we plug in for delta x and delta y? dx dt delta t and dy dt delta t. So what do we end up with? We end up with this line right here. All we've done, what is this right here? That's delta x, and what is this right here? That's all. This is just substitution. This is, hold on. This is just substitution. What's in this line here? What do you see in both places? Delta t. What can you factor out? Delta t, and then what can you divide both sides by? Delta t. So what do we now have? dz dt, the rate of change of z with respect to t is this partial z, partial x dx dt, partial z, partial y dy dt. And the hardest thing to do is to keep track of all of it, right? Because this is just the simplest way possible. How many input values are there for x and y? Just what? Just t. Just t is going into both x and y. Could there be more? Yes. So all this means is that you have to have a system for keeping track of all of the partials. And I'm going to give you a system. And it's fun. It's a treat. I think it's pretty fun. Do you understand the math we did right here? Are you going to have to do this every single time you do a partial in terms of the input, original input? No, you're not. But I need you to understand the process here. Understand the process. So what is that tree? You ready to see a pretty picture? This right here is the blue box version of what we just did. If f, g, and h are differentiable, if z equals f of x, y, and x is g of t, and y is h of t, then, hey, look, does that look familiar? That's exactly what we just figured out. That's the exact same thing.
Can someone tell me when you use this little partial and when you use this d? When do you use the partial and when do you use the d?
Multivariable.
Multivariable, exactly, when there's more than one choice. What about dx, dt? Oh, x was solely written in terms of t. Exactly. Okay, so here's the tree that you get to see. Yay, tree time. So z is written in terms of x and y. Y is written in terms of t. So the first thing you do is you draw this tree diagram. Everybody sees this tree diagram? And then what do you write between them? The connecting partial. Connecting partial, connecting derivative, correcting derivative. So if you want dz, dy, what do? You find all of the paths, sorry, dz, dt. The way I do it is I circle where am I starting and where am I ending. And then what do I draw? All of the what? All of the ways to get there, exactly. And then what do you do with all of those paths? You do the product. So what's the purple path? Partial z, partial x, times what? Dx. I got to be careful. Dx, dt. And then what's the other path? Partial z, partial y, what? Dy, dt. And what do? Add them. So you make your tree. You circle the start and the end. And then you just do the products of the paths added together. So can it get more fun? Sure, but let's exercise this thing first, okay? Let's exercise this thing first. And we have a total of 2 minutes, so we can get through this next example here. It says, suppose that z equals f of xy, x sine y, where x is equal to this. Oh, y. Oh, is this nice at least? X is written in terms of t, and y is written in terms of t. Let z equal g of t. Compute g prime. Okay, directly using the chain rule. 2 times x cosine y. There it is. There's your derivative. Does that kind of make sense, everybody?
Yes.
Does that kind of make sense? Ish?